range, fall off and damping values for that as well. The orbital speed is a tangential force that in combination with the radial pull force below gives our particles their characteristic circular motion. This force generally has to be carefully balanced with that of the radial pull. If you increase the orbital speed, more radial pull is needed to stop the particles flying off into space, and this works in both directions, so you really do have to balance those two forces. Below this we have range, and this, as with the previous force, axial drop, is a range which actually goes out from the central axis in this case of the actual icon. So it's a cylindrical range, with its center being based on that of the actual icon itself. The fall off again is a cylindrical fall off, and again the axis is based on the center of the icon. Again you have a damping value, and again that stops any sort of excessive acceleration of particles. It'll stop them going above a basic speed basically when you increase this damping value. Next we have radial pull, which we can see here. And the radial pull subforce is a form of cylindrical gravity that actually acts in concert with the orbital speed subforce to produce the circular motion of the particles, as I just mentioned. In general, you'll want the range of this force to exceed that of the orbital speed force, as this will keep the particles pulled within the actual range of the orbital speed. If you have a smaller value than this, the orbital speed will cause particles to spin outside this range, and spinning particles will actually move away from the center of the force, and effectively they'll escape its influence. So you always want the radial pull to be actually bigger than the orbital speed ranges. Next we have the clockwise and counterclockwise toggle boxes. As you can see, you've got these radio buttons, and what they do is they actually decide the direction of the actual rotational forces, basically the orbital speed. You can actually change the direction using these two values here, either clockwise or counterclockwise. Now let's try and isolate some of these actual forces so we can see them more clearly with the force viewer. The first thing we'll try and get rid of axial drop. I'll get rid of damping, and I'll actually put that down to 0. If we look from above, we can see we have these snapshots through the force, and you can see that you have above, you can see you've got these very weak forces, rotational forces, and here you can see you've got these much stronger rotational forces, and that's caused by the orbital speed, which you can see here. If I increase the orbital speed, you can see you've got a much stronger orbital vortex going on there. I'll just drop that down again, and then on top of that then you actually have the radial pull. If I put that into 0 and now I increase it again, you can see at 0 the particles will only actually be spun around the axis, and actually that will actually throw them outwards. So you need a radial pull value to actually pull the particles inwards, and you can see that being reflected here with these vectors, which you can actually see here. You can see where you get to the tapered point of the vortex, you can actually see again much more sort of pinched values, and it's a little bit more relaxed up here. So you've got much more sort of loose rotation here, and it goes down into a tighter cone as it goes down here. So if we turn axial drop back on, you'll see they also get pulled downwards. You can see here we can actually pull our particles downwards, and let's actually see this in action now by turning on our particle flow. I'll just freeze this so it's a little bit less visible. Turn on our particles. There they are. They're all available to be pulled into this vortex, and we'll just see how it works in action. So there you go. You can see the particles above are being thrown outwards by this rotational force. I think at the moment the problem is the actual orbital speed is way too high, so let's actually make some adjustments to try and get that to be a little bit nicer. We'll knock down the orbital speed. Try that. Again, that's very powerful. Let's actually reduce that even more. Okay, and let's see that now. It's looking a little bit better. The radial pull, let's actually reduce that some as well. And let's also increase our damping somewhat. Okay, let's try that now. So there you go, you can see our particles are being dropped downwards. We need to drop the actual drop actually quite a bit, otherwise it'll be too drastic. There we go. Now if we press play, there you go, you can see our particles are being pulled inwards. I think at the moment again our radial pull is too high. So let's try it now. Now you can see our particles are being pulled inwards, and they're also being rotated. As you can see here, they're starting to form a vortex shape. And as you can see, that it's a very, very difficult force to work with, because you've got all these different options here to try and create a nice vortex shape. when you get these balanced, you will actually get a nice vortex forming. As you could see in that particular example, it actually was starting to form quite a nice vortex at the end there. But actually, counterbalancing all these options is actually very difficult to do on many occasions. And I've done quite a bit of R&D into the actual vortex force, and I've found that it actually doesn't work very well when you have multiple vortex forces. And that's because vertically it actually has no limit to the effect that it has on particles. So if I was to extend this particle box off into a massive height up here, you'd actually see this vortex taking place right off into infinity. So personally, I prefer to actually use a combination of other forces to produce the same effect. And talking of those other forces, let's just stop this here, put it back to beginning. Let's move on now and have a look at the particle bomb force.